Okay, can everybody see my screen? Just want to double check before I start talking. Okay, great. Thanks, Sean. Perfect. All right, so let's see here. Again, I posted this PDF in the chat if you want to print it out or if you want to follow along on a tablet. Well, let's look at these questions. These are questions that I handpicked, and I thought they would make an effective review for Chemistry 3111. Student asked me a couple of semesters ago, why do we even have to write at a final exam in Chemistry 3111? Well, I think you would be remiss to not have some kind of comprehensive review of everything that you spent a year learning, before finishing up the class. Okay, well, question number 1, onto which of the numbered atoms in the following structure can the negative charge be moved by drawing resonance structures? So we have numbers for all the carbons and the oxygens, and we just want to see where this negative charge can be delocalized. So basically, this question is about drawing resonance structures, right? Can you draw effective resonance structures? Well, let's try drawing them out ourselves. So this is the first question. I'll redraw the structure here for you because you're going to need a little room to give this one the old college try, so to speak. So we have the negative charge here on our oxygen. So this is some kind of phenoxide derivative. And then we have two aldehydes over here like this. So this is something that you've done a lot of over the course of the year, is drawing resonance structures and curved arrows with many mechanisms. So let's just give this one a go here. I'm going to start by moving the electrons down here, and I'm going to break this pi bond and put the electrons over here. So let's see what that's going to look like. So there we go. So we're going to erase that and this, and then we'll end up with something that looks like this, and we'll have our carbanion here. All right. Then we'll worry about the numbers after. All right, let's draw another curved arrow for our resonance structure here. So we're going to form a new pi bond here, and we're going to move these electrons over here like that. So let's draw what that would look like. It'll look something like this. I have my negative charge up here. Everything is still conjugated, of course. That. Okay. So this was carbon 6. This one is carbon 4. Anyhow, I'm just kind of following along here. Now we can move that negative charge around some more. So let's do that. So we'll make a new bond here, and we can put our carbanion on this carbon. So let's draw what that will look like. And we're going to have our double bond here, our aldehyde, and our carbanion will be there. And then there's one more resonance structure that we can draw. We're going to move this pair of electrons over here and put it down on this oxygen. And there we go. And that's going to give us, again, the final resonance structure, which will look like this. So we have negative charge here. This aldehyde was never touched throughout the entire process. And there we go. So these are the 4 resonance structures. Now, again, if we label all of these elements, so this is carbon number 2 here, and then this is element number 8 or atom number 8. So the answer is 2, 4, 6, and 8, right? Who do we appreciate? Anyhow, those are the 4 atoms that can take on the negative charge, starting with this anion here. Okay, now something that you notice is, you might look at this structure initially and say, well, I've got a negative charge in this oxygen. It's going to end up on this, on this oxygen, but it doesn't, right? So you have to draw, you would definitely need scratch paper to solve this problem. All right, so 2, 4, 6, 8. So the answer is C. All right, let's move on to number 2. Just a little bit about pKa's. And hopefully you memorized some pKa's throughout the course. I recommended that at the very beginning of Chemistry 3101 to familiarize yourself with some pKa's. So we've got A, B, C, D in here. And it's just asking you which one would have the smallest pKa value. You might want to solve this one using Aereo, or I think it would actually just be easier to solve it using, memorization, because they're all carbon-hydrogen bonds, right? They're just on, differently hybridized carbons, right? Here we have an sp hybridized carbon. This one is sp2. This one is sp3, and this one is sp2. All right. Well, I mean, out of all of these, can anybody tell me? Does anybody have a knee-jerk reaction as to which one of these is going to have the lowest pKa? There's one of them that's a lot more acidic than all the rest. Yeah, thanks, Sean. The answer is D, right? Because an alkyne or an acetylenic hydrogen is going to have a pKa of around 25, right? Whereas all these other ones are kind of going to be in the neighborhood of around 40 to 45. So these will all be in the neighborhood of 40 to 45-ish, okay? All those sp2. But an sp3, remember that since an sp hybridized, sorry, did I say sp3 when I'm at sp? An sp hybridized orbital is smaller, right? You can't go off of atom. That doesn't work. You can't go off resonance. You can't go off induction, but you can go off orbital here because these are all carbon-hydrogen bonds, okay? And that's the way we solve this. And since an sp orbital is a lot smaller than an sp2 or an sp3, it's going to provide the most stabilized carbanion, and therefore it's the most acidic, smallest pKa value, right? And you should know the smallest pKa value means most acidic. All right, let's look at number 3. Which Newman projection best represents the most stable conformation of this molecule? Well, first, I think I will start out by drawing the bond line structure of this molecule. You can see that it's got a 4-carbon chain, so 1, 2, 3, 4, like this, and then I have a methyl group here and a methyl group here. So the compound is 2,3-dimethyl butane, okay? Now, I'll give you a second to look at these structures and see if you can figure out which one is the most stable conformation. Excuse me. All right. Does anybody notice anything, really unreasonable about any of these structures? Because a lot of questions on an ACS exam, and again, we're not writing the ACS exam, but a lot of these type questions, that you would see on an MCAT or a DAT or an ACS, a lot of them can be solved by process of elimination. Is there any structures here that just look totally unreasonable? Right. So somebody says B and D are the wrong compound. I agree with you 100%, Andrew. These are not the right compound, are they? Why? Because you can see here, this is a tert-butyl, right? That's a tert-butyl, and in the back on this one here, we have a tert-butyl. So those aren't the right compound, okay? Now A and C, they both are the right compound. They're both 2,3-dimethyl butane. But how would we differentiate between A and C as to which one is the correct answer? Well, if we're looking for the most stable Newman projection, we're going to look for the one that minimizes gauche interactions, right? Remember that gauche interactions are this kind of interaction here, where we have a dihedral angle of 60 degrees, between these two methyl groups. So we have a gauche interaction here, we have another one here, and another one here. So here we have 3 gauche interactions. Whereas in this one here, we only have 2 of them. We have 2 gauche interactions. And so C is going to be the correct answer. It's the most stable Newman, most stable conformation. All right, well, let's move on to number 4. Which resonance form best explains the greater acidity of Terra nitrophenol relative to phenol. Okay, now if we think about, if we think about paranitrophenol versus phenol, so this is question number 4. Phenol looks like this, and phenol has a pKa of around 10. We'll just say pKa equal to 10. Why is that? Because when you deprotonate, right, the conjugate base is resonance stabilized, and you could practice drawing all those resonance structures. But paranitrophenol, right, if I draw paranitrophenol, and you should know how to draw a nitro group, right? A nitro group, Lewis structure, has 2 charges. It has a positive charge on the nitrogen and a negative charge on the oxygen. Okay, so this is paranitrophenol, and if we draw its conjugate base, let's do that. What you're going to see is that it's going to be resonance stabilized, but it's going to be even more so resonance stabilized. Okay, now again, we could draw all the resonance contributors for phenol, right? What we're going to see is that you're going to end up with a negative charge on this carbon or a carbon on here. You're going to end up with one here and one here as well. Now the same thing applies to the paranitrophenol. Its conjugate base, if we drew all the resonance structures, you'd have a negative charge here, negative charge here, negative charge here too, okay? But the thing is, it has one additional resonance structure, doesn't it? Right? It has a resonance structure where we can draw and show the negative charge is being delocalized down on an oxygen, or down on an oxygen in the nitro, okay? And that is what's going to contribute to its greater acidity, right? What's an acid? Something that donates a proton. How do we qualify acid strength? Well, it's whatever is going to produce a more stable conjugate base. And since this base, or this conjugate base rather, has an additional resonance structure where it shows where we have the negative charge delocalized down on that electron withdrawing nitro group, this explains why paranitrophenol is more acidic than phenol. So that resonance structure is shown here. It's C, where we see the negative charge down here. Okay, I mean, if you look at this one, that doesn't help us with anything. That just draws the first, you know, the deprotonation. That's just shows the conjugate base, but it doesn't explain, right, the greater acidity of paranitrophenol. Okay, same thing with this one. I mean, I could draw an equivalent resonance structure with phenol, okay, but it doesn't explain why paranitrophenol is so much more acidic, right? Only C does that, and if you look at D, well, that's just plain wrong. All right, well, let's move on to number 5, which asks us which molecule has the R configuration. So we have to evaluate all of these using the Kohn-Ingold pre-log rules. By now, I imagine you're pretty quick at this. I'll give you a second to see if you can figure out which one of these has the R configuration. If anybody figures it out, just type it in the chat. Yeah, Sean's got it. It's C, right? C is R. Well, let's take a look at all these kind of quickly. And again, I'm not going to reteach Kohn-Ingold pre-log rules. I'm sure you all know them by now. But if you look at A, the hydrogen's in the back. It's the lowest priority. It takes 4th priority. You have the oxygen directly attached, so that's going to take priority 1. Then you've got 2 carbons here. This one is attached to 2 oxygens, so we got 1, 2, and 3. So we're going to follow it going this way. And since we're going counterclockwise and the lowest priority group is in the back, this has an S configuration. If we move to the next one, this is going to be lowest priority. The oxygen is 1st priority. The carboxyl group is going to be 2nd highest priority, and the CH2OH is going to be 3rd highest priority. If we follow that, that's also counterclockwise, so that's S. If you look at D, okay, if we look at D, We're going to start with the oxygen being highest priority, the hydrogen's lowest priority. It's in the back. This carbon is attached to nitrogen, nitrogen, nitrogen. This carbon is attached to hydrogen, hydrogen, hydrogen. So obviously the nitrile is going to be number 2. This is number 3. So we go from 1 to 2 to 3. That's counterclockwise. So this is S. Then when we go to this alcohol here, you look at the chiral carbon, there's no hydrogen attached to it. But if you evaluate all 4 of the substituents, you see the methyl group is the lowest priority in this case. So it's number 4, and it's pointing in the back. The oxygen is going to be number 1. If you evaluate this carbon, it's attached to oxygen, oxygen, hydrogen. And if you evaluate this carbon, it's attached to oxygen, hydrogen, hydrogen. So our tiebreaker is going to be this oxygen right here. And that means that this will be our second highest priority group. This is number 3. So we're going 1, 2, 3 in this direction. That's clockwise. And so this has an R configuration. Okay, number 6 is a little more practice with stereochemistry. This is nothing more than a definition. It says, what is the stereochemical classification of 1s2s, 1,2-cyclohexane diol, and 1r2s cyclohexane diol? Well, you see that everything else is the same, right? They're both 1,2-cyclohexane diols, but one is 1s, 2s, and the other one is 1r2s. And so they differ in their configuration at one stereocenter. Can anybody tell me which one of these would be the best definition? Yeah, so Andrew says that these two are diastereomers, right? When we have stereoisomers that are, so if we have stereoisomers that are not enantiomers, so if they differ at one stereocenter like this, we can call those diastereomers. All right, now if you had to draw the compounds out, that's totally fine too, because one of them is a meso compound, but they can't both be meso compounds. If you draw the 1r2s, which I did, you know, 1r2s looks like this. If we had a hydroxyl here and a hydroxyl here, sure, that's a meso compound, but 1s2s is not a meso compound, and so these are diastereomers. Okay, so this is 1r2s, and this is 1r2s. No, sorry, 1s. My mistake. 1s. There we go. All right, so diastereomers. Number 7, about cis and trans, it says, or asks us which is capable of exhibiting cis-trans isomerism. I'll give you a second to think about that one. Evaluate these structures. Great. Somebody says B. I tend to agree with that. I think that's the right answer. The first one is an alkyne. So an alkyne cannot exhibit cis-trans isomerism. It doesn't exist, right? If you look at C, it is an alkene and it can exist, but it can't have cis-trans isomerism. Why? Because on one of the carbons, the carbon on the left here, you have 2 methyl groups. And when you have 2 groups that are identical on the same carbon, cis-trans isomerism is impossible. And then if you look at the last one, we have this is called an allene. So allenes don't exhibit cis-trans isomerism, whereas the compound in B, 1,2-cyclobutane diol, that can exist is cis-trans isomers, can it, right? If we have the cis, that's a meso compound, and then we could also draw, a trans compound for it too, okay? Like this. Okay, there we go. So that one can have cis-trans isomerism. Anyhow, good enough. Number 8 asks us which Newman projection corresponds to point A. So this point right here on the graph of potential energy versus rotation about the carbon-2, carbon-3 bond. And if you look at all the possible answers here, you see that the molecule is butane. All right. So what we're doing is we're looking at the rotation around the carbon-2, carbon-3 axis. The first thing I think we should do is evaluate, what's going to be the lowest energy, and then we have whatever is going to be the highest energy. If you look at all of these, you see that these two conformations are staggered, and these two conformations are eclipsed. So that means that A and B are going to be maxima, right? They're going to be the peaks, okay, on this curve. So that means that A and B are going to be here and here. Answers A and B, right? This is point A. It's kind of confusing the way they did it. They could have called it X. It would have been way smarter. Anyhow, so the maxima are going to be represented by answers A or B. Now, if you look at the two of them, you see that we have a gauche interaction here between the two methyl groups. And so B, how can I color code this? The easiest, okay? So B is going to be up here. So this is going to be structure B, okay, or molecule B is maybe what I could call it, or answer B. I don't know. So dumb. And then A is going to be this one here. So this would be answer A. So the two staggered conformations, those are going to be the two minima. If I look at the two of them, you can see that this one here, D, has one gauche interaction. And so since D has a gauche interaction, it's going to be higher in energy than this one here, where the two methyl groups are anti-periplanar from each other. And so answer C, answer C is going to be here, and then answer A, this is going to be point A is going to be answer D. So the correct answer is this one here. All right. Also, something that I think I might have said incorrectly was that I called this a gauche interaction. It's not a gauche interaction. Those are eclipsed. So when they eclipse each other, right, it's going to be high energy. Okay, give me a thumbs up if you follow me on that problem. We looked at dihedral angles back in Organic Chemistry 1, but remember, this is a comprehensive exam that covers everything you've learned in organic chemistry. So I'm kind of going back in time here to refresh our memories. All right, number 9, what is the relationship between these two structures? What's the relationship between these two structures? I'll give you a second to think about it. If anybody comes up with an answer, just feel free to type it in the chat. Andrew says C. All right, they're definitely not identical molecules, are they? It can't be A because you see we have 1, 2 here for our diol, And here we have 1, 2, 3. I mean, there's a bunch of ways you could approach this problem, right? But they're definitely not identical. And so somebody else, or sorry, B says conformational isomers. Conformational isomers means you change the conformation. That means the two molecules would have to have the same connectivity. These don't even have the same connectivity. Now the next one says stereoisomers. Stereoisomers also have to have the same connectivity. They just have different arrangement of their atoms in space. So these molecules are connected completely differently, but they both have the same molecular formula, right? They're both C6H12O2. And so they have the same constitution, even though they have different connectivity. And so they are constitutional isomers, those two molecules. The first one would be trans 1,2 cyclohexane diol, and the second one would be cis 1,3 cyclohexane diol, if you want to just go by their names. Okay, next question involves reactions. You know, if you ever wonder, okay, well, how can I be asked, you know, multiple questions about reactions in one question? Well, here's an example of them doing it, right? It says, which reaction would proceed the fastest? If we look at A, we have ethyl methyl ether, and we're treating that with hydroxide. And they're saying, okay, we're going to get an SN2 like this, okay, like that. And there's a bond here that's not shown, and then you would lose the methoxy. And the second one, you have ethyl methyl sulfide, and you do something similar. So then it's based off of, you know, what would be a better leaving group, you know, a methoxide, or the sulfur with a negative charge. The next one, we have an amine. Okay, so that's just loony, but anyhow, right, you'd get an SN2 like this. And I'm kind of drawing the bosine here quickly. And then if you look at D, anyhow, let me give you a second to think about all these. Well, if you see the little note that I've made here, what do all these reactions have in common? They're all the structures of the substrates are an ethyl group with a leaving group attached, and then a hydroxide is coming in and you're doing an SN2. Well, so really all we're doing is we're evaluating, you know, which would be the best leaving group. The methoxide, I mean, I think I should highlight, which one of these is the best leaving group out of all these things that I have highlighted in green? Well, since these are all bases, the conjugate acid of the conjugate base of the strongest acid is going to be the best leaving group, right? So the question is, which one of these is the weakest base? You know, another way you could put it is, which one of these has the most stabilized negative charge? My question to you now is, does anybody recognize this part right here? Does anybody recognize this? It's something that we looked at. You might not be used to seeing C6H4 like that, but what I have circled in red, that's like saying this. So you've got O, you know, and then you have C6H4 represents the aromatic ring, and then you've got a methyl group attached to it like this. So this is a tosylate, OTS, okay? So this is OTS minus. And tosic acid is a really strong acid. You look up tosic acid, toluene sulfonic acid, it has a pKa of around -5. And so its conjugate base is going to make the best leaving group out of all of these, right? If you think about the conjugate acid here, methanol, that would be around 15. Conjugate acid here would be around 7, and the conjugate acid here would be around, like, what, 35 or something. So this is by far the best leaving group. So this is going to proceed faster than any of them by a long shot. Yeah, exactly. Thanks, Sean. Tosyl, right? Toluene sulfonyl. Okay, what is the expected product of this reaction? This is just a lithium aluminum hydride reduction. Before I answer it, I'll give you a second to look at it. Do some computing in your brain. All right, well, let's try and draw a mechanism for this reaction. So here we go. We'll draw this. And if you're wondering what the D is, that's just deuterium, which is hydrogen 2, right? It's just a hydrogen with a neutron in the nucleus. All right, there we go. So now we've got lithium aluminum hydride. Draw the structure of the aluminum hydride ion, like that. And that's going to deliver a hydrogen. Well, I've got two places where I can do, add the hydride, right? These two carbons that I have highlighted in red. But which one is it going to attack? Well, it's going to go for the least hindered one, right? Because I have an oxirane or an epoxide. And if you remember, epoxide opening with lithium aluminum hydride will occur at the less hindered carbon. And if you're thinking, well, hey, what about when didn't it attack at a tertiary sometimes? That was an acid catalyzed ring opening, right? That's something completely different, okay? So let's see what's going to happen here. We're going to have our hydride come in and attack the least hindered carbon, but it's going to attack from the top face, right? Attack from top. Why? Because you've got the oxirane down at the bottom, which takes up more space. And so when I open the ring like that, the oxygen is going to be on the bottom on this carbon, and this is going to push the deuterium down, right? So when we draw the product, it's going to look something like this. Okay, so let's draw it. So that means our methyl group here is still going to be pointing up. Now we're going to have our oxygen pointing down, right, with a negative charge, like that. And our deuterium will also be pointing down, and our hydrogen is going to be pointing up. So that shows you why they put the deuterium in there. It's so that, they can test you to make sure that you understand how the nucleophilic attack is going to occur. And so if I protonate this with water, so a little bit of acid, okay, that's going to give me C. That's my final answer. So this is, quizzing you on epoxide. So if you need to review your epoxide chemistry or oxirane chemistry, be sure to go ahead and do that. That was in the ethers and epoxides chapter 13. Okay, let's talk about transition states for a sec. Says, which of these structures best depicts the transition state for the reaction of iodomethane with methoxide, potassium methoxide in methanol? So if you think about the reaction that's occurring here, we're taking methoxide, which would be our nucleophile. I'm going to draw, iodomethane showing the hydrogens of the showing the tetrahedral structure, right? And then I have my methoxide that's going to behave as a nucleophile, and it's going to do an SN2, right? This is an SN2 reaction. So that's what they're asking you here is, do you understand SN2? Why? Because SN2 works with a good or a strong nucleophile, like methoxide, and we have a strong base methoxide, and then we have a methyl halide. So that's going to have a good leaving group, and that's going to proceed by an SN2 mechanism. So if you need to go back and look at in our textbook, so this is covered in figure 7.20, the whole summary of analysis of substrates and nucleophiles. But again, that's going to give us an SN2 reaction, which is going to proceed with inversion of configuration, right? So what's the transition state going to look like? Well, the transition state is going to look like something like this, right? A transition state is the transition period where we have this bond being formed between the oxygen and the carbon, and then we have a bond being broken from the carbon to the iodine. Now, keep in mind it's not a chiral center, but you still get inversion, a flip of these hydrogens, right? They were on this side, and then they're going to be on, they're going to flip over like this, okay? Anyhow, again, it's not a chiral center, so it's neither here nor there, but the idea still stands. Okay, so this is just testing, do you understand what an SN2 reaction is? And if you're like, oh man, that's a tough question. Well, I mean, look at the other answers. They're so out in left field. I mean, this one just shows a methide. That's nothing. This one shows an oxygen bound to a potassium. I mean, that's just plain wrong. And this one here, I can't even figure out what the hell is going on in this one. That is just wacky. I think I'd like to know what the person had for breakfast that morning. They've got two bonds to a hydrogen, and yikes, a doodle. Anyhow, all kinds of crazy stuff going on there. Anyhow, give me a thumbs up if D is cursed. Yeah, D is, you know what, Andrew? Sometimes they come up with some wacky answers, and that's cool. That's cool. But this one, I would say, is one of the wackiest things. That just makes no sense at all. I can't even imagine a student of mine coming up with that and being like, here's an idea, All right. When I said, what were they having for breakfast? I was going to say, what they're smoking, but I stopped myself. Okay, well, let's try another problem. This one here, number 13, is a question I think I asked on a quiz this semester or something almost identical to it. This, again, comes from chapter 13. The ethers in a pot. The Texas hydrogen. That's right, David. Did I teach you guys about the Texas carbon? When you have a carbon with 5 bonds, don't draw that, but they call that the Texas carbon. What I didn't learn that until I came to the States, but in Canada, we always said when anybody drew that in a job interview, we just said, thanks for coming out. It's been great. And we go into the office. Like, what the hell was that? Where was I? Number 13. Look, we're treating this compound with excess HBr. Well, primary and secondary alcohols, when you treat them with HBr, they're going to be converted to an alkyl halide, right? So if you think about, what the heck is going on here, right? If you have RCH2OH and you treat that with HBr, right? The first thing is that it's going to get protonated, right? Converted to a good leaving group. So then you'd have this RCH2OH2 plus, right? So now you've got a good leaving group, and then bromide can come in and behave as a nucleophile. I'm really drawing shorthand mechanisms here. And then you would get, you get a primary alkyl bromide. Okay, so we know that this is going to be converted to a bromide. So this looks good, this looks good. So that means these two, we can eliminate them. But remember that when we have an ether, we're going to break those ether bonds as well when we treat it with an HBr. And both of these carbons, if I highlight them in yellow, let's say, so this carbon and this carbon here, those are both going to have a bromine attached to them. And we looked at the mechanism of that. So that would mean the correct answer is this one here. Now, I think one of the questions that I asked on your quiz, or something that we went over in class one time, I'll show you. And this is important, so that's why I'm spending, a little bit of time on it. Let me just clean this up here. There we go. Let me see if I can get some more real estate here. So what I'm talking about is this, and this is, again, something that we looked at in class in detail, is if you take, now let me start with cyclohexane. So if you were to take ethoxycyclohexane and treat that with excess HBr, what would you get? You'd get cyclohexane bromide, okay, plus you'd also form ethyl bromide. Okay, good. If you took ethoxybenzene Okay, and hopefully you remember this. And you did the same thing, treat it with excess HBr, you're going to end up with phenol. Okay, so you don't get, bromobenzene, you get phenol. And the reason why is because you're not going to form an sp2 hybridized carbocation, right? Those are highly unstable. So you would end up with these two as your products, okay? So I think, they put the cyclohexane ring in there to kind of throw you off. Even now, sometimes I'll have students messing up cyclohexane and benzene, which you shouldn't be doing at this point, but I see it once in a while. Anyhow, so that's it's cleavage of an ether. So cleavage, and ether. Yeah, there we go. All right, let's try number 14. Identify the possible products of a dehydrohalogenation of trans 1-bromo 2-methyl cyclohexane. You know what? Why don't I just redraw this compound? You know what? No, I don't need to. I don't have to. I can explain it to you. I don't want to reteach everything. So what I was going to do is I was going to go to a blank document for a second and draw a chair, but there's no need. You don't have to draw a chair here, okay? Because you're treating this secondary alkyl halide, right? We have one leaving group in the whole damn thing, and we've got a strong base. So this is going to be an elimination. I mean, look at all these double bonds in here. Obviously, it's something about elimination, isn't it? You've got hydroxide. Okay, so here's your base. Okay, there it's ripping and ready to go. Now, if this is the carbon with your halogen attached, you can either pull a proton from here, maybe, or you can pull one of the protons from here. So it just comes down to a matter of, which protons can I remove? I have a question for you guys. I want to see what you remember. If I circle this proton in red, can I remove that proton with the hydroxide? Can I do an E2 reaction here? Is that a possibility? Let's see, what did somebody say? Somebody says no, right? Sean says no. I agree with you, Sean. You can't do it, right? The reason why you cannot abstract this, the reason why I can't draw this curved arrow, so don't draw this, right? Don't draw this at home, okay? The reason you can't do that, that's a big no-no, right, is because that hydrogen is not anti-coplanar to the bromine, right? Remember, on a ring, the leaving groups, the hydrogen in the leaving group, when you do an elimination, they have to be anti-periplanar, anti-coplanar. I like anti-periplanar because anti-coplanar refers to it's exactly 180 degrees. What if I draw these two hydrogens in, right? I've got one going down, and then I've got another one coming up, like this. Well, this hydrogen is anti-coplanar. Maybe I'll circle it in a different color. Anti-coplanar. So that means I could rip off that hydrogen, okay? So I could eliminate this guy, and then I would make a double bond here, and I would lose my bromine. Now, I don't have a lot of space here, okay? But hopefully you can see what the heck is going on. So that means I'm going to form a double bond right here, okay? And I'm going to have no double bond there whatsoever. Now, if you need to redraw the compound, this is why scratch paper comes in handy. You just redraw the 6-membered ring like that, and you say, okay, well, I'm going to have a double bond here, and then I'm going to have my methyl group pointing down like that. Okay? Now, they left all the stereochemistry at that stereocenter, they left it out in the possible answers, right? It says, identify possible products. And so you really can only get this one product, which is A. It's the only possibility. Okay? So what they're trying to get you to do is they're trying to trick you into drawing choosing both of these ones in B. But remember, you can't. Why does that always go away? You can't form this product, and it's because of that hydrogen that I have circled in red, which is not anti-coplanar. So things to think about, right? What are they asking in this question? A couple of things. They're asking if you understand E2 reactions, and they're asking if you understand an E2 reaction on the cyclohexane. So it's kind of up a notch, right? It's not just a regular old straight chain E2 reaction. All right, let's try number 15. 15 is just a pure memorization problem as far as I'm concerned. Which molecule will complete the reaction shown below? I'm going to see my finger in here. Anyhow, I'll give you a second. Think about this one. If you have an answer, just go ahead and type it in. So we have water, sulfuric acid, and mercuric sulfate. Yeah, thanks, Diego. Yeah, the answer is you got to have an acetylene derivative, or sorry, alkyne, right? Because when we treat this terminal alkyne with those conditions, what do you end up with? You end up with this compound. Let's draw it out. You actually form an enol, don't you? You form an enol that looks like this. So you're doing a Markovnikov addition of water across that triple bond. Right? It's nothing more than a Markovnikov addition, but this enol is going to undergo tautomerization to give you the methyl ketone. So, right, and that's a methyl ketone right there. Okay, so a few things here. You got to remember the reaction. So hydration of a terminal alkyne, we produce an enol, and that undergoes tautomerization to give you a methyl ketone. So synthesis of a methyl ketone. All right, we're steaming along here. Okay, let's try another one. Hey, some Diels-Alder chemistry. This is chapter 16 in our book. So if you need to review your Diels-Alder chemistry, so chapter 16, it says which reagents can the ketone shown be prepared via a Diels-Alder reaction? With which reagents can the ketone shown be prepared via a Diels-Alder reaction? So, I mean, really, you could draw the Diels-Alder products. This one won't work because this is a 2+2 cycle addition, right? A Diels-Alder is a 4+2, right? If you forgot the Diels-Alder reaction, it's something like this. So you draw your curved arrows like this. That's going to give you, my last curved arrows are kind of wonky, but you get the idea. There you go. So that's a Diels-Alder reaction. This next one here, this is a 4+2, but that's going to give you a bridged compound, right? If you draw those curved arrows, right, like this, and then this, that's going to give you a compound with a bridge in it, so that's not right. This one is also a 2+2, whereas this one, if I draw my curved arrows, right, like this, so if I draw curved arrows like this, and this is going to give me the desired product. So it's a matter of knowing what a Diels-Alder reaction is, and then being able to discern, you know, which what's my diene. So my diene in this case is just going to be 1,3-butadiene in the S-cis conformation, and then this will be my dienophile. Okay, so Diels-Alder chemistry, if you need to review that. Number 17. Yeah, I'm going to give you a second to look at question 17. It takes a minute to digest it. Which reagent sequence will affect the transformation shown? So if somebody asks you to do this, said I want you to start with this bromide and I want you to make this alkene. Okay, here are your reagents. In what order do you throw them in the reaction flask? Okay, you start with this. Do you add 1, 2, or 3 first? And in what order do you put the other reagents? So I'll give you a second. Does anybody have an answer for this one? Could anybody name the reaction? All right, somebody says C. Does anybody have a name for the reaction, this reaction? Yeah, it's the Wittig reaction, right? Awesome. Perfect. All right, so we're going to start out. Why don't we just draw the whole damn thing? So this is our starting material. 2-bromopropane or isopropyl bromide, however you want to think about it. So what do we need to do? Well, we're going to need to make a Wittig reagent, aren't we? All right, so the first step is we're going to treat that with triphenylphosphine. All right, so we're going to treat that with triphenylphosphine. Just going to do an SN2 reaction. Then we're going to end up with a phosphonium salt. Looks like this. Right, like that. And then we're going to abstract this proton using a base in order to make our ylide. So the base that we're going to use, C4H9. The C4H9, that's the same thing as a butyl group, right? A butyl group, 1, 2, 3, 4. Right, so butyl lithium is this, okay? So butyl lithium is our base. And let's just write it like this, butyl lithium, which is a really strong base. All right, we don't want to use that in the undergraduate lab because it's pyrophoric. Anyhow, there we go. Let's draw the ylene. So then we have our ylene, which looks like this. And if you want to draw the ylide, that's totally fine too. All right, and then we have our carbonyl compound. And if you want to practice, drawing the mechanism of the Wittig reaction, by all means do so. And I'll let you finish that anyhow, but that's a Wittig reaction, right? We get our oxetane, then it undergoes decomposition to give you triphenylphosphine oxide. So let's see, the first one is reagent 2, then 1, so it's 2, 1, 3. So that is C. All right, so make sure you know the Wittig reaction and any other big important reactions that we looked at. Number 18 deals with kinetic products. So it says, which is the major kinetic product produced in the reaction shown? So this is just addition of HCl, a 1,2 addition, right? Remember that kinetic addition gives you the 1,2 product, the 1,2 addition, like that, okay? And, well, what's going to give us the most stable carbocation here? Would it be adding a hydrogen on here or on here? And the answer is, if we add the hydrogen from our HCl, if we add it to this carbon, right, like that, then we're going to end up with a tertiary carbocation, right? The only possible tertiary carbocation that we could get, right? And then the chloride is going to come in and act as a nucleophile. And we're going to end up with this product. So we're going to have our double bond here, and that's our 1,2 product. And that is B. Give me a thumbs up if you follow me on that. Kinetic addition, really important. It's something that we looked at in detail over this semester. This is an organic 2 concept. Let's see here. Hey, the next one. Oh, where did I go? Getting ahead of myself. Okay, the next one's just it says, which is the best reagent for this conversion? I'll give you a second to look at it. Remember that D just stands for deuterium. It's just an isotope of hydrogen. And the reason they put those in there is to make sure that it's a way for them to test you, to make sure you understand the mechanism. So say, for example, it says D2O. That's just, water with deuterium replaced. And you have sodium borodeuteride. That's the same thing as sodium borohydride, except you have deuteriums instead of hydrogens. NaOD, that's just, deuteroxide, which would just be this instead of, hydroxide, right? This is deuterium peroxide, which is, again, just like, so they want to test you to make sure you understand the mechanism. So let me give you a few seconds to think about that one and see if you can come up with an answer. Question 19. All right, Andrew says B. All right, let me see here. It is the correct answer. So what are we doing here? We're doing a reduction, and if I was to treat this with water containing catalytic amounts of HCl, that's not going to do a reduction. Sodium boron-deuteride will do a reduction. We'll look at the mechanism. It says it's in ethanol. And an aqueous, it says and an aqueous workup. That just means to provide this proton here. The next one is using a strong base. So that would just act as a nucleophile. That's not going to produce a reduction. And then if you look at hydrogen peroxide in acetic acid, that's not going to do a reduction either. Okay. I just want to go over the mechanism of this one kind of quickly with you guys, just to make sure we're all on the same page on reduction, sodium boron-deuteride reduction. So this is question number 19. Let's start by drawing out the cyclopentane carbaldehyde. So remember, we have a dipole going this way, or we could say the oxygen is delta minus and the carbon is delta plus, like that. Then we have sodium, so NaBD4. So the borodeuteride is going to look like this. And it's going to have a negative charge. And so that's going to act as a reducing agent to put the hydride here. And then our intermediate, our tetrahedral intermediate, will look like this. So on the carbon, we've got a hydrogen. Now we've got a deuterium, and we have our oxygen with the negative charge. And then it says that you treat that with water, right? So water is going to behave as a base, right? And then you're going to protonate here, and you're going to end up with this compound. So you'd have a carbon with a hydrogen and a deuterium, and then you have your oxygen with a hydrogen attached. Okay, and so that is the answer is B. So we go back here to question 19. Yeah, the answer was B. All right. Number 20. What's the expected product of this reaction? Remember that when we have an ester in a ring, we call that a lactone. This is called a lactone. So basically this lactone, or this cyclic ester, is being treated with lithium aluminum hydride, followed by an aqueous workup. So I think one of the best things we could do here would be to draw a mechanism for this reaction, right? In order for us to figure out what's going on, unless anybody else is, or unless anyone is able to, figure out what's going on here, right? If you just memorize, okay, if I take an ester, right? If I take an ester like this, we'll call this R prime, and I treat that with lithium aluminum hydride followed by an aqueous workup, right? What am I going to get? I'm going to end up with an alcohol plus. I'm also going to end up with this alcohol, right? So that would make it really easy. I mean, that would just tell you that the answer has to be D, because you're not going to have an aldehyde that would be reduced, right? It's not going to be cyclic, and you'd have to have two oxygens, so it can't be that. So the answer is D. Okay. In the interest of time, I'm not going to draw the mechanism, but it's a mechanism that you need to know. Lithium aluminum hydride reduction. And the mechanism that we look at in chemistry 3111 is even an abridged or simplified mechanism of, the reality, right, where the lithium behaves as a Lewis acid. Anyhow, so make sure you know the mechanism of lithium aluminum hydride reduction mechanism. Okay. Number 21, hey, something near and dear to our hearts, right? Polymers, something that we just looked at the other day. So question 21, which of these polymers could be readily prepared by the condensation polymerization? So which one of these would not be an addition polymer, but rather a condensation polymer? I'll give you a second to look at it. Yeah, Skylar says A, and she's 100% correct. Yeah, it's definitely going to be A, right? What would the molecule be that you would use to make that polyamide, right? Well, you could practice drawing it out. You're going to have a quiz on it in a couple days, so it would look like this, right? The bifunctional compound, you have a carboxyl group and an amine, and so you would just make amide bond after amide bond after amide bond, right? All the rest would be made by addition or some other kind of mechanism. This one here is the most obvious, right? Because you would make an amide, right? You would keep repeating, right? Anyhow, so on and so forth. All right, so that's going to be a condensation polymer. You lose water in the condensation reaction, form an amide. Let's see, which base should be used quantitatively? Quantitatively means completely, so 100%. Which base should be used to quantitatively convert N-dimethylamide into its enolate? So if we want to deprotonate this and convert it into its enolate, it's going to look like this. Yeah, we want to convert it into this, so we want to remove one of these protons right here. Well, I'll give you a second to look at these. Let's see, what did Sean put? C. Yeah. Do you remember what the acronym for C is, Sean? Does anybody remember what the acronym for this base is? There is an acronym, and we did look at it in the enols and enolates chapter, which is chapter 21. This is called LDA, lithium diisopropylamide. Okay, LDA. Well, if you look at all these bases here, lithium acetate, lithium methoxide, lithium diisopropyl amide, and lithium hydroxide, right? Which one of these is going to be the strongest base? Well, the easiest way to evaluate their basicity is to look at the acidity of their conjugate acids, right? And whichever one has the weakest conjugate acid is going to be the strongest base, right? The weaker the acid, the stronger the conjugate base. So the conjugate base, or sorry, the conjugate acid of A is acetic acid, which has a pKa of around 5. The conjugate acid of ethoxide is ethanol, which has a pKa of around 16. The conjugate acid of hydroxide is water, which has a pKa of 15.7. But the conjugate acid of an amide is an amine, right? Would be diisopropyl amine. And that's got a pKa of around 36, okay, much higher. And if you're like, well, I can't remember exactly 36, as long as you remember that an amine is up in the 30s, right? You can see how that's a much weaker acid than any of the rest. So since it's the weakest acid, it's got the strongest conjugate base. And so the answer is LDA is going to be the best choice there. All right. Number 23. What would be the major product of this reaction? This also comes from the enols and enolates chapter. Enols and enolates alpha carbon chemistry. So this is chapter 21 material as well. This one's one you got to be careful with. This is an aldol addition reaction. And if you're wondering, how did you know it was aldol addition and not aldol condensation? Because remember, aldol condensation, we would treat the aldehyde. What happened there? Somehow I lost everything. Dismiss. Somehow I've lost my chat. Oh, here we go. Yeah, this is an aldol addition, and the reason why it's an aldol addition is because there's no heat applied. No heat. Okay, if there was heat, then it would be an aldol condensation reaction. So let's give this one a try. We'll start by drawing out the aldehyde. So 23, so CH3, CH2, CH, and I'm going to explicitly draw that hydrogen for instructional purposes only, right? And we're going to treat that with our base, so our hydroxide. Remove this proton and make the enolate. So let's draw what the enolate would look like. Like that, and that's going to react with another molecule of the aldehyde. I'm just going to draw it in a different way here. 2, 3, there we go. Then we're going to get our addition like this, like that, which is going to give us this intermediate. It's going to look like this: CH3, CH2, CH, the aldehyde, and then it's going to be attached to this carbon, which has the oxygen with a negative charge. That's CH2, CH2, CH3, and then that's going to react with water in order to abstract a proton. That, and that's going to give us our product. Now I'm going to draw it a little bit differently. I'll draw it the same way we have shown it in the book. So, why the hell would I do that? All right, we're going to end up with this product. Let's just draw the following line structure. So, I have this guy, my alcohol here, and then I have 1, 2, 3, like that. So that's the product of the aldol addition. Again, this is aldol addition. So see chapter 21. So if we go back to our answers, the best answer is, or the correct answer is C. All right.